All right, y'all, let's get excited. We're going into graphing motion now. All right, so this is nothing new. We have already been looking at motion on graphs the entire time that we have been doing one-dimensional motion. We started this unit with our walking directions lab, and if you look around the classroom, you can see all of these distance versus time graphs that are graphing motion. All right, so that's exactly what we're going to be talking about today. All right, so motion graphs, the reason we show motion graphs is because they are showing the relationship between our position in time, our velocity in time, and our acceleration over time. All right, so it's just a super easy way to see how that velocity, that position, or that acceleration is changing over time. All right, so these are our three types of motion graphs that we are going to be talking about. Position versus time, that's going to be the umbrella term that we use for them. We see them along the walls on our graphs as distance versus time graphs. All right, we also know that it's the same thing as a displacement versus time graph. Okay, so all three of these are the exact same thing. All right, so they are just showing how our person or our object is changing its position over time. It's changing its distance over time. It's changing its displacement over time. All right, so a position versus time graph, a distance versus time graph, and a displacement versus time graph are all the exact same thing. You do need to know that because it's going to change. All right, you're going to see it all three ways. So you need to know that they are all the same thing. All right, so what we're going to be working on today is turning those position versus time graphs into velocity versus time graphs. And then we're going to eventually turn these velocity versus time graphs into acceleration versus time graphs. All right, so it's just going to be looking at the motion. We're going to be describing what's happening. All right, so we know that these position versus time graphs, these are the most basic graphs that we can show for motion graphs. All right, so they just show how an object is changing its position over time. So with a position versus time graph, we know that we have three different types or three different shapes of a position versus time graph. All right, so we know that if we have a horizontal line on a position versus time graph, that means that the object or the person is not moving. Okay, we know that a horizontal line means it's not moving. If we have a straight diagonal line, that means that we have constant motion or constant velocity. And then if we have, let's see here. All right, so if we have a curve of some sort, that means that we have a changing velocity. And we haven't gotten there yet, but we will eventually. We'll look at it today. And if we have velocity that is not constant, it is changing, this is something called acceleration. Okay, so we have acceleration. All right, so these are the three things that we can see on a position versus time graph. You do need to know what these three shapes mean on a position versus time graph. All right, so we have already graphed all of these different things. So right now, I want you to look at this motion of the car. If we look at this motion, so at 0 seconds, it is at position 0. So that's going to be our first point. Okay, so that's the point at the origin. All right, this car, after 1 second, travels 10 meters. At 2 seconds, it's at the 20-meter mark. At 3 seconds, it's at the 30-meter mark. At 4 seconds, it's at the 40 meter mark. And at 5 seconds, it's at the 50 meter mark. So if we were to graph all of those points on a position versus time graph, it would look something like that. All right, so after 1 second, so this would be our first point. Technically, our first point would be at the origin, 0, 0. All right, so at 1 second, it was at 10 meters. At 2 seconds, it was at 20. At 3 seconds, it was at 30. 4 seconds, it was at 40. 5 seconds, it was at 50. All right, so that is what we would see. Okay, so if we drew our best fit line, all right, I don't have a ruler or anything. I'm doing my best. Yes, okay. All right, so we see a straight diagonal line. All right, let's go back up here. What do we know a straight diagonal line means? It means that we are going at a constant, or we have a constant motion. All right, we have already talked about how the slope of a position versus time graph is going to be measured in meters per second. That is going to be our unit for velocity. So we know the slope of a position versus time graph gives us a velocity. All right, so if we were to actually solve for slope, remember that slope is equal to our change in y over our change in x. So that's going to be y2 minus y1 over x2 minus x1. We can plug in any of those numbers, and we are going to get a plus 10 meters per second. So every single second it traveled 10 meters, all right, is what that says. Now we add that plus because we know velocity is a vector quantity and we know it's going in that positive direction. So we add that plus to it. A positive slope on a position versus time graph means it's going in the positive direction. All right, so slope is what tells us, again, the slope of a position versus time graph gives us our velocity. So say that this is our slope for 10 meters per second. That blue line is the slope for our graph right there. All right, if we have a line that is lower, you saw this on your graph, on your lab, the other day. All right, if we have a line that is less steep, that means that it is traveling slower. The velocity is slower. If we have a line that is steeper than our slope, than our line, then that means that it is traveling faster. So the steepness of the line can tell you which one is traveling faster than the other. All right, so, oh no, I hate this. All right, so I'm going to do my best on this. If you go to your actual PowerPoint that's on Schoology and pull it up, it will show you this. I'm going to do my best though. All right, so the blue car, we're going to see, we're gonna see a line that maybe looks like that, and then you're gonna see a red car pop up, but it's not gonna start until 4 seconds. So we're gonna see a line that looks like that. Okay, so if we are looking at these two lines, there are a lot of things that I can tell just by looking at these two lines. All right, the first thing that I can tell is the position that these cars start at. So the blue car is starting at that 20 meter mark, and that's what you see right here. You see him starting at the 20 meter mark. So you see that the red car, the red line, starts at the 0 on the y-axis. And so that means that the red car is going to start at that origin, at that original position, that 0 meter mark. All right, what you're going to see next is that the blue line starts at time 0. So it starts at the beginning. That red line does not start until that 4-second mark. So that means that the red car does not start until 4 seconds. So the blue car starts at the beginning, 0 seconds. The red car does not start going until 4 seconds. All right, the next thing that you can see is that we have two diagonal lines, two straight diagonal lines. That means that the blue car is going at a constant velocity as well as the red car. So again, if we see a straight diagonal line on a position versus time graph, that means that we have constant velocity. It's not changing its velocity. Okay, so the next thing that we can notice is that the red line is a lot steeper than the blue line. So that tells us that the red car is going significantly faster than the blue car. Now, the next thing, the last thing, I guess, that I want you to see is this point right here, the point where they intersect, okay? So if we are trying to figure out what that intersection means, so does that mean that they're going at the same speed at that point? No. All right, so I want you to say no. So we know that they are going at a constant speed that entire time. That red car is going at its greater constant speed. The blue car is going at its slower constant speed. So they're never going to be going at the same speed. That point just means that they are passing the same position at the same time. So that just means that they're going to be side by side at that point. They're at the same position, but they will never be going at the same velocity. Okay? All right, so here we're not creating a graph. Here I've given you a graph and I want to know what this graph is saying. All right, so we have two different segments. So we have the segment from 0 to 5 is doing one thing, and then from 5 to 10 is doing another thing. So we're gonna have like we'll say segment A right here, and then segment B right here. All right, so again, we need to pay attention. We are looking at a position versus time graph. So what do we know is happening on a position versus time graph if we have that straight diagonal line? Okay, so if we look at the points, all right, so after 1 second, we're at the 5 meter mark. At 2 seconds, we're at the 10 meter mark. At 3 seconds, we're at the 15 meter mark. At 4 seconds, we're at the 20 meter mark. And then at 5 seconds, we're at the 25 meter mark. And then 6 seconds, we're still at the 25. 7 seconds, we're still at the 25. 8 seconds, we're still at the 25. 9 seconds, we're still at the 25. 10 seconds, we're still at the 25 meter mark. Okay? So if we look at what's happening with these points, we can kind of interpret it. All right, so we know that a straight diagonal line means that we have a constant velocity. We have that constant positive velocity for those first 5 seconds. And then from 5 to 10 seconds, it stays at that 25 meter mark, which means that it is not moving. It is standing still. Okay, so part B means it's not moving. Part A means that we have a constant velocity or a constant motion. Okay, so what I want you to do right now is I want you to calculate the slope for both parts. All right, so for part A, slope is y2 minus y1 over x2 minus x1. So we can pick any 2 points. It does not matter because they're all on the line. All right, so let's do this one and this one. So we have 20 minus 10 over 4 minus 2. Okay, so 20 minus 10 is a positive 10. 4 minus 2 gives us 2. All right, so we know that 10 divided by 2 is 5. That plus just tells us it's going in the positive direction, and it's going to be meters per second. All right, so the slope for that first part, for part A, is going to be a positive 5 meters per second. What is the slope of part B? Is it moving? Is it rising anywhere? No. All right, so the slope for part B is going to be 0 meters per second. Okay, so that's its velocity. So we know that the slope of a position versus time graph gives us velocity. All right, so what I want to introduce to you right now is a velocity versus time graph. It's a velocity versus time graph. So this is what a velocity versus time graph looks like. All right, so your time is still on the x-axis measured in seconds, and your velocity is on your y-axis. Most of the time it's going to be measured in meters per second. So what you see right here is at the origin, that means that your velocity is 0. Above the 0, you see a plus. That means you have a positive velocity. Below that 0, you see a negative. That means you have a negative velocity. Well, what does a positive velocity mean? It means you're going in the positive direction. What does a negative velocity mean? It means you're going in the negative direction. And we can find that on our position versus time graphs. Okay, so let's plot this. So let's take what we just learned from this position versus time graph. So our times are going to be the same. So we go from 0 to 10. So let's do that same thing. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh no, I did it too. Let's start over. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Did a little too close that time. It's fine. We're fine. Everything's fine. Okay. So we're only looking until 10 seconds. So for the first 5 seconds, we have a constant velocity of 5 meters per second. So that means after 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is going to be a positive 1, positive 2, positive 3, positive 4, positive 5. This is going to be a negative 1, negative 2, negative 3, negative 4, negative 5. Okay, so from 0 to 5 seconds, it's at 5 meters per second. So that means after 1 second, it's going to have a speed of 5 meters per second. After 2 seconds, same thing. 3 seconds, same thing. 4 seconds, same thing. 5 seconds, same thing. Okay, so what does a constant velocity look like on a velocity versus time graph? If we draw our best fit line, we see that. Okay, so we have a straight horizontal line at positive 5 meters per second. That shows a constant velocity of a positive 5 meters per second. All right, well, what about from 5 to 10 seconds? What was our slope? It was not moving, so the speed of something that's not moving is 0 meters per second. So how would we show that on here? At that point, at this point, it's all 0 meters per second. So we draw our dots, we draw our points at 0 meters per second. We draw our best fit line. So we have 2 horizontal lines. So this is the velocity for part A. This is the velocity for part B. So we would have them on the same graph. They would just be 2 different segments. You're not going to connect them. If you did want to connect them, you would draw just a dotted line going down, a vertical dotted line to connect them. Okay? All right, so that would be a velocity versus time graph for this motion. So we can see that at this point, Okay, at the first part A, it was going at that constant velocity of positive 5 meters per second. At part B, it was not moving, and we know that the speed of something that is not moving is 0 meters per second. So that's what we would see. Okay, now this graph is looking at the graph that we made right here. Okay, so we found that from 0 to 5 seconds, it moved at a constant velocity of 10 meters per second in that positive direction. So what you're seeing right here is the velocity versus time graph for that position versus time graph. So after every single second, it was still going 10 meters per second. So we see that horizontal line at 10 meters per second. Okay, so a constant velocity is shown as a straight horizontal line on whatever number that is. Okay, let's see. Okay, this is just putting them together. We just did that. Poop. This is the one. Okay, so if you were going to go back to that PowerPoint, you would see this actually playing out. All right, it doesn't play out on my iPad. So if we are looking at a constant positive velocity, so this little dot is our person or is our vehicle or our object, whichever one it is. All right, how would we show that it was going in the positive direction? We would go from left to right. So we know this dot is going to be traveling to the right. How would we show a constant velocity? That means that these lines would all be equidistant apart. So I'm going to do my best making these all equally separated. All right, so please forgive me if they are not 100% perfectly separated equally. All right, but that's what we would see. We would see dots that were equidistant apart. Okay, so what would that look like on a position versus time graph? Well, we know if it's going in the positive direction, it's going to be a positive slope. Constant means we're going to see a straight diagonal line. Okay, so that would be a straight diagonal line. Now, if we were to calculate the slope of this, I'm just gonna, okay, this is gonna be 5, 50 first 10, okay, it's a little over 10, so we'll just say it's like a 12, all right? So we know that it's a constant velocity, it's in the positive direction, and it's at about 12. Okay, so our velocity versus time graph would look like that. It would just be a straight horizontal line at the positive 12 point. Okay, now we know that the slope of a position versus time graph is measured in meters per second, which is velocity. Now, velocity versus time graph would give us meters per second, which is acceleration. All right, so you will see it as meters per second or meters per second squared. All right, we're going to get into that later. All right, but what I want you to see right here is that if I calculated the slope for this velocity, it's 0. There's no rise in it. So we would have no acceleration. So, oh, no, I did not want that. I wanted it to be at 0. So let's see if I can do a little bit better here. There we go. Yes. Okay. So the slope of a position versus time graph gives us velocity. The slope of a velocity versus time graph gives us acceleration. So this is what a constant positive velocity is shown. This is how it would be shown on all 3 of these different graphs, okay? So again, we're just showing the motion of objects using these graphs. All right, so here we're looking at a constant negative velocity. So again, negative direction means it would be going from left to right. Constant just means that our dots would be equally spaced. I think this might be worse than the last one. I apologize. Okay, so what does that look like on a position versus time graph? All right, we know it's a constant velocity, so it's going to be a straight diagonal line. It's going in the negative direction, so it's going to have that negative slope. Okay, so it's going to look like that. Okay, if we find the slope of a position versus time graph, that gives us our velocity. So we know it's going to be negative. We're going to say that this is about the same as the last one. So we'll say it's going to be not a positive 12, but a negative 12. All right, so if it's a constant, that is shown using a straight horizontal line at that negative 12 mark. And we know that the slope of a velocity versus time graph gives us acceleration. Okay, well, there is no slope there. It's 0. So that means that our acceleration graph would just be a straight horizontal line on 0. Okay. All right. So if we are looking, all right, so we're going back to the blue car and the red car. So what we did earlier, all right, whenever I drew it out, was a position versus time graph. Okay, remember that these are going at constant velocities. The blue one starts at 0, the red one starts at 4 seconds. All right, and we can tell by the steepness that the blue line is going slower than the red line. Okay, so we could calculate these out. I am not, just for the sake of time. All right, but if we were to graph these, all right, our time is still the same. So our blue line, let's just say it starts here. Okay, so our blue line would be a constant velocity of about, what is that, like 5.5, I guess. So it would look like that. And our red line, our red car, remember, did not start until 4 seconds. So we're not going to start until the 4 seconds. And it was, say, like 16. Okay. So a velocity versus time graph for that position versus time graph for those two cars would look something like this. Okay, it does not take into account their position at all, just the times that they started. All right, so you can't tell their starting position from a velocity versus time graph, but you can tell their velocity. All right, so those two horizontal lines means we have a constant velocity. They're above 0, so they're going in the positive direction. And that red line is higher than the blue line, so that tells me that it's going faster than the blue car. The red car is going faster than the blue car. All right, now this is the last thing. All right, so I want to know first, again, we're looking at two separate segments on the same position versus time graph. All right, so I want to know what the slope is at point A, or during A, part A. All right, so we know that it's not changing position, so our slope for that is 0 meters per second. It is not moving. If we find the slope at B for part B, let's see, it dropped 10, so that's negative 10 divided by 2. So our slope for part B is negative 5 meters per second. We know that it's a constant velocity because we've got that straight diagonal line. So if I want to sketch a velocity versus time graph for this, let's go ahead and draw our velocity versus time graph. Okay, so we have time measured in seconds. We have velocity. And since our position versus time graph was measured in meters per second, we know that our velocity is going to be found in meters per second. This is 0. Up here is positive velocity. Down here is negative velocity. All right, so we can go ahead and do the same times. Remember, they have the same corresponding times. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. All right, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. Oh, not 2 20s, 22. Okay. All right, so for the first 10 seconds, we have a slope of 0. That means that it is not moving. So the first part of this is going to be at 0. So it's not moving, so it's got a speed of 0. So the first part of this velocity versus time graph is going to be at 0. Well, we know that for the next 10 seconds, it's going at a constant speed of -5. All right, so we'll just say that -5 is down here. So at 10 seconds, it starts going that -5 meters per second. So we have a constant velocity of -5 meters per second. All right, so we're not going to do this on two separate velocity versus time graphs. All right, we're just going to do two different segments on the same graph, okay? What if we turn this, I know we're jumping ahead, but it's super easy right now. What if we turn this into an acceleration versus time graph? Because we know that the slope of a velocity versus time graph gives us acceleration. Again, this is our time, and we do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, well, that's great. All right, so I went up. So acceleration is going to be on our y-axis. If the slope of a velocity versus time graph is our acceleration, that's going to be measured in meters per second or meters per second squared. We have 0 up here. We have a plus up here, negative down here. And what do we notice? What would the slope be for both of those lines? Are either one of them rising? No. All right, so the slope for this, let's get a little Christmassy. The slope for this entire graph is just going to be at 0. That tells us that we have no acceleration whatsoever. Okay. All right, so this is our first little part of graphing motion. If you have any questions, you know where to find me.